Hi everyone, I'd like to present our ECCV 2024 paper titled Restoring Images in Adverse Weather Conditions via Histogram Transformer. We first discuss our motivation. We noticed that the weather-induced degradation patterns tend to be similar but distinct from the background. However, the existing networks do not utilize this prior knowledge, and traditional self-attention is performed either along channel dimension or within a fixed range. So we categorize pixels affected by adverse weather and background pixels into distinct bins based on descending intensities, and then conduct self-attention within and between the bins. The overall structure of our proposed model is a U-Net-like multi-scale encoder-decoder. Within each stage, it contains multiple histogram transformer blocks called HTB. We used pixel unshuffle and pixel shuffle operations for the purpose of feature downsampling and upsampling. We also add 3 crude skip connections to focus more effectively on learning the weather-induced residuals. Within HTB, there are layered norms, dynamic range histogram self-attention called DHSA, and dual-scale gated feed-forward module called DGFF. Inside the DHSA, we developed a technique of dynamic range convolution. It splits features into 2 parts and sorts the second part horizontally and vertically. Then a separate convolution is applied. At the end of DHSA, the feature pixels of the sorted second part will be reordered back. This step will enable convolution layer to process dynamic range receptive fields thanks to the similar pattern prior knowledge of weather degradation. After the dynamic range convolution, we introduce histogram self-attention. There are 2 kinds of it. The first is the bin-wise one, which is to assign pixels into a finite number of bins according to the pixel values, and then perform self-attention among the bins. The second one is the frequency-wise histogram self-attention. It is to assign feature pixels into bins which a finite number of frequencies belongs to. We split features of query and key into 2 branches and apply the 2 kinds of histogram self-attention on the 2 branches. The 2 branch features are then fused by a pixel-wise product. Within a DGFF module, we leverage a 5x5 depth-wise convolution and a 3x3 dilated depth-wise convolution for dual-scale operation. The dual-scale convolutions are then fused by gating mechanism. Before and after the operations, we use pixel shuffle and unshuffle for channel spatial interaction. Here we show the overall architecture of our Histoformer for adverse weather removal. For loss function, we notice that the existing pixel level reconstruction loss neglects the patch level consistency. So besides the L1 norm as the reconstruction loss, we introduce Pearson correlation coefficients to ensure the preservation of intensity relationships. We experiment our Histoformer on 3 adverse weather removal tasks, including image desnowing, heavy rain removal, and raindrop removal. For all the 3 tasks, our method attains overall the best results. We also conduct multiple ablation studies on the choices of dynamic range, convolution, self-attention, feed-forward modules, and so on. We configure our model based on the ablation studies, and they also validate the effect of our proposed modules. We also show several visual comparisons on the adverse weather removal tasks. Several zoomed-in details are shown alongside. We can see our method achieves the most pleasing results. Here shows the visual results of real-world adverse weather removal and its downstream object detection application. Our method effectively removes the real-world snowflakes and helps the Google API detection model recognize additional objects like a door and a building. Thank you for your attention.